Hey guys, finally anhydrous perchloric acid on YouTube! I spent an entire month preparing the material for this video. I hope it was worth it. Enjoy, leave your comments, and I won't keep you with small talk. Let's get started. The first thing I did to obtain anhydrous perchloric acid was to assemble a vacuum distillation setup and use it to distill the 60% perchloric acid I had on hand. I filled the distillation flask with the acid. For vacuum distillation, a special capillary is inserted into the second neck. If the distillation is performed at atmospheric pressure, the acid partially decomposes, releasing chlorine and oxygen and turning pale yellow, which is highly undesirable for the preparation of the anhydrous form. I seal the top of the flask with a thermometer, circulate water through the condenser, apply vacuum using a water aspirator pump, and heat the oil bath containing the distillation flask. If you cannot monitor the vacuum with the manometer, initially small bubbles in the flask that gradually grow indicate that a good vacuum has been achieved in the system. After some time, water begins to distill into the first receiving flask. Once water has been removed from the perchloric acid and its concentration rises above 70%, the azeotropic mixture at that concentration starts to distill. As a result, we obtained pure, transparent perchloric acid with a concentration of approximately 70%. Then I repeated the same distillation with this acid and obtained the maximum achievable concentration of perchloric acid at about 72%. The accurately measured amount of 72% perchloric acid must then be cooled to a very low temperature. To achieve this, I prepare an ice bath from acetone and dry ice. When adding more dry ice to the acetone no longer produces vigorous boiling, it can be considered that the lowest achievable temperature for cooling the acid has been reached. And the next step is to add highly concentrated oleum to the acid. Let me remind you that oleum is a solution of sulfur trioxide in concentrated sulfuric acid, so let's prepare it. For this, I'll have to sacrifice this beautiful ampoule containing sulfur trioxide. The ampoule is strong enough to allow the sulfur trioxide to be melted inside it. The thing is that under normal pressure, sulfur trioxide is very difficult to melt, because it's likely to sublime instead, which is why it's melted under pressure whenever possible. Moreover, it remains liquid for quite a long time. Look here. This mobile liquid is the liquid sulfur trioxide that we need in order to prepare oleum of the desired concentration. I add the measured volume of liquid sulfur trioxide to the concentrated sulfuric acid using a drop-in funnel while keeping the mixture cooled. When all the sulfur trioxide has been added to the sulfuric acid, we'll obtain oleum at a required concentration. This pale brown liquid is 60% oleum, which we will add to our 72% perchloric acid. In general, the most important aspect in the synthesis of perchloric acid is accurately calculating the required amounts of oleum and perchloric acid. The idea behind combining oleum with perchloric acid is to obtain a mixture that corresponds to pure 100% perchloric acid and pure 100% sulfuric acid. Oleum removes water from perchloric acid, increasing the acid's concentration, and in turn lowering its own concentration as it is converted into sulfuric acid. If the oleum concentration is too high, it will dehydrate the anhydrous perchloric acid, driving the formation of the highly dangerous chlorine heptoxide. If the amount of volume is lower, the perchloric acid will not reach its highest possible concentration, and the yield will also be lower. Take a look at the liquid in the flask. It's an ideal mixture of 100% perchloric acid and 100% sulfuric acid. There is no water present, and it's from this mixture that the anhydrous perchloric acid will be distilled. I pour this acid mixture into a drop-in funnel, which is connected to this rather interesting glassware setup, so let me tell you a bit more about it. The main component of this glassware setup is this long glass tube wrapped with nichrome wire, which is connected to an adjustable transformer, allowing the temperature of the wire to be controlled by changing the voltage. I want to point out that all the joints in this setup are individually ground to provide a vacuum-tight seal, meaning they fit perfectly together without any gaps. This ensures an excellent vacuum in the system, so there is no need to use PTFE tape. This is a very important detail for this synthesis. A bend tube is inserted into the central neck of this tube, which allows controlling the plane in which the U-shaped receiver tube for the perchloric acid will be positioned. This is the tube in which the anhydrous perchloric acid will be collected. Look, this joint on the U-shaped tube fits perfectly with the corresponding joint on the bent tube, so you get a perfect vacuum. Nothing else is needed, no grease, no PTFE tape. Naturally, the perchloric acid will be collected at reduced temperature, so it also needs to be kept in a dry ice bath. The dry ice I'm adding to the acetone is a bit dirty because it was stored in a contaminated container, so the bath takes on this orange-brown color, but it doesn't affect anything. So I place the prepared bath under our receiver. This time I switch on the vacuum pump instead of a water aspirator pump. I also apply voltage to the wire, heating it and thus creating a system temperature of around 70 degrees, which is ideal for this synthesis. Then, in periodic portions, I introduce our acid mixture into the system. After the acid mixture enters the tube, it heats up, and the vapors of the perchloric acid are carried out of the system by the vacuum, condensing in the U-shaped receiving tube. Since the main glass tube is positioned at a small angle, and the temperature of the tube is not high enough to evaporate sulfuric acid vapors, so it, together with the remaining unevaporated perchloric acid, drains into a separate flask. Thus, I believe that this is the safest possible method for obtaining perchloric acid. Only a minimal amount of the mixture is present in the reaction zone for a short time, and the temperature does not allow the perchloric acid to begin dangerous decomposing. All other methods require significant heating of the perchloric acid, which will almost always turn it yellow. So, after several hours, we can check what we have obtained in our receiver. As expected, we obtained perfectly pure, transparent anhydrous perchloric acid. In fact, liquid perchloric acid is partially dimerized, and it exhibits an equilibrium cell dehydration. Let's take a moment to admire it before moving on to the chemical reactions. This transparent liquid contains a great deal of potential energy that will soon be releasing. So, perchloric acid needs to be stored at a very cold temperature, so I'll transfer it into a flask, which I will keep in dry ice. Look at how much anhydrous perchloric acid fumes, unlike the concentrated solutions we are used to. Anhydrous acid behaves very differently from its solutions. Look, I made a black background so the heavy acid vapors would be more visible. Here are slow-motion shots of perchloric acid droplets falling. So now that we have anhydrous perchloric acid, let's finally take a look at its reactivity. And the first thing we will test is its sensitivity to impact. According to literature on perchloric acid, pure perchloric acid doesn't detonate from impact or friction, but I decided to verify this myself. Yes, there was no explosion, but a small flash is visible in one frame. Therefore, I cannot fully agree about its insensitivity to impact. Now let's heat perchloric acid strongly. We've all heard that when heated, it darkens and then explodes. So let's take a look at that. I'll just leave a heat gun next to a test tube with perchloric acid and move to a safe place. Interestingly, immediately after the tiny explosion, the remaining perchloric acid turned colorless. Why do you think that happened? Write your thoughts in the comments. Perchloric acid also didn't explode when its drop was placed on a heated metal surface. It initially turned yellow, then red, and finally yellow again before evaporating. The thermal decomposition of anhydrous perchloric acid proceeds through the formation of chlorine heptoxide. Above 60 degrees Celsius, it produces oxygen and various chlorine oxides, which are responsible for the red and yellow colors observed during its decomposition. I found these shots really interesting in slow motion, so I added them too. But that's everything regarding the pure perchloric acid. Now let's see how this acid reacts when it comes into contact with other substances. First up, a cotton glove. Indeed, no other acid behaves like perchloric acid with this material. Concentrated sulfuric or selenic acid would only char such a glove without causing any explosions. Notice that in all these experiments I'm using very cold acid, and it still reacts so vigorously. So this is what happened to the glove after a few drops of perchloric acid. By the way, if you add a few drops of perchloric acid on indicator paper, it will instantly char. Next, a more interesting reaction – potato chips. Really, what will happen if we drop a few drops of perchloric acid onto a chip? Wow, the explosion was so powerful that it punched a hole in my sturdy porcelain stoneware table. This is undoubtedly the most powerful acid any of us have ever come across. Next, let's add a few drops to a sugar cube and see what happens. The reaction with sugar resembles that of sulfuric acid, leading to charring. The key difference is that, unlike sulfuric acid, it produces easily flammable carbon. That was a sugar cube, but what happens if we add a few drops to a sweet Oreo cookie? Yes, this reaction is different from the previous one. It crashed yet another one of my tables. Of all the possible acids in their pure form, not in mixtures, only selenic acid can dissolve gold, but sometimes you come across information suggesting that perchloric acid can do this as well, so I decided to find out and share the results with you. For the first reaction I used a few small pieces of gold foil and concentrated perchloric acid. I brought the acid to a boil and heated the gold in it, but it didn't dissolve. The solution turned yellow because perchloric acid breaks down when heated. Then I took another small piece of thin gold foil, but this time I added anhydrous perchloric acid and began heating it. After the perchloric acid turned red and boiled for a while, the gold was still lying at the bottom of the test tube unchanged. Then I added a little water, and it became clear that the gold hadn't dissolved even in the anhydrous acid. Thus, for now, I still cannot say that there is any acid other than selenic acid that could dissolve gold. So let's move on to the other reactions, and next we have an interesting one involving potassium permanganate. When a few drops of perchloric acid are added to potassium permanganate, after some time a mixture of brown and green fumes begins to appear, followed by a small burst that splashes the mixture. Next, I tried dropping some perchloric acid onto my hair, which I had washed thoroughly before test, so a vigorous reaction should occur. And here is how perchloric acid reacts with a regular kitchen sponge. Cigarette tobacco accumulates very high levels of lithium compared to other plants. That's why perchloric acid reacts with a cigarette, producing the characteristic crimson color of lithium ions. The reaction of perchloric acid with wood looks very interesting, but before showing that, let's first take a look at how it reacts with other cellulose-containing materials. Here is what it does to cotton wool. Next in line is toilet paper. I also tried to light a match using perchloric acid, but it didn't ignite, even though sulfuric acid lights a match quite easily, so in the end I just lit it normally. And now let's take a look at the reaction with wood, but before that, let's see how it reacts with sawdust. If I drip cold perchloric acid onto a smooth wooden surface, it instantly chars, but there is no explosion. However, the acid behaves completely differently when it comes into contact with a rough surface. It seems that perchloric acid is completely incompatible with carbon, so for next reaction I prepared a jar filled with activated charcoal. In the comments under the previous video you asked for a chemical unboxing, so here it is, enjoy! Well then, let's take a look at the reaction with carbon powder. It took several drops of perchloric acid to make the watch glass shatter. Maybe with other substances a single drop will be enough. So this is phenylacetylene. Great, one drop was enough. What about anhydrous hydrazine? But first, let's take a look at the reaction with hydrazine hydrate. And now anhydrous hydrazine. So guys, that was the video about perchloric acid. I'm sure you liked it, and spoiler, I've already filmed another video about perchloric acid, where we test explosive properties of different materials soaked in it, so make sure to subscribe so you don't miss it. And if you can, consider becoming my patron on Patreon, the link is in the description. Thanks to you, videos like this are possible. And you can also send us super thanks by clicking the button right under the video. It really helps a lot, and I appreciate every single one of you who does it. Thanks for watching, see you in the next video.